Hello friends, today we are going to learn graph searching algorithms. Remember that in previous class under decrease and conquer strategies, we have learned what is decrease and conquer and a different types of decrease and conquer approach. Under that we have learned one algorithms called insertion sort algorithms. Today let us discuss what is graph searching algorithm. Name itself is what? Graph searching algorithms. It means graph could be one of the kind of input. So if for the given graph, say we have a 4 vertex, 5 vertex or 10 vertex, whatever it is, we are going to find out whether all the nodes are connected with each other or not, or some particular node is reachable from the source node or not. Right? So those kind of discussions you are going to make on the graph search algorithms. And under this we are going to discuss two different algorithms. One is called DFS and other is BFS. Okay, depth first search and breadth first search. Now, remember that when we wanted to give input as a graph to the program, then it's not possible to give direct graph as an input. So there is a way we can give at the place of graph, we can give adjacency matrix to the input to the program. And I believe most of you will be aware of what is adjacency matrix. So let us see that what is adjacency matrix, and thereafter we will start discussing that graph search algorithms. So let us consider here we have 4 nodes A, B, C, D. There is a connectivity between the nodes. Okay. Like this. So we can see that it is called directed graph since there is certain directions on the edge. In that case, if we wanted to give this particular graph as an input to the program, then we must convert this graph into another form. And what is that? Either adjacency matrix or adjacency linked list. So here we are going to see what is adjacency matrix. So look, if there is in direct edge, from I to j, then we will be writing 1, right? Otherwise we will write it 0. And what is when we will give 1? A of ij is equal to 1 only when there is path from I to j. So remember that I and j is a vertex. So we are saying that A of ij will be 1 only when there is a path between the vertex. A of ij will be 0 if there is no edge from I to j. So there are two ways, either you are going to write 1 or you are going to write 0, right? When there is a path is there or not there. So in this particular case, if you wanted to write adjacency matrix, what will happen? You are going to write A, B, C, D, A, B, C, D. It is the name of the vertex. Look, A to A, it is source to source vertex. We are writing 0. If there would have self loop, and A is connected with some edge vertex, will be edge, or you can say the path, then we will be writing here 1. Since there is no edge between A to A, we will be writing 0. Source to source 0. A to A 0. A to B, you can see that there is a path. A to B 1. A to C, here is a C. A to C we don't have direct edge, so hence it is 0. A to D, there is a direct edge, so it is 1. Similarly, B to A we don't have, so we are writing 0. B to B 0. B to C, similarly there is a path from B to C, hence it is 1. B to D, You can see there is no direct path, hence it is 0. C2A, no path, 0. C2B, 0. C2C, 0. C2G, 0. D2A, no, it is 0. D2B, yes, D2B there is a path, 1. D2C, there is a path, 1. And D2D, again you are writing 0. So this is called here adjacency matrix. When there is an edge between the vertex, write it as 1. If there is no edge between the vertex, write it as a 0. So like this, we are going to give input to the program, and we are going to discuss this kind of graphical examples by applying BFS and DFS. We will apply breadth first search and depth first search to find connectivity between the nodes, or you can say the vertex, or you can call it as a cities. So let us discuss what is depth first search. Remember that name itself is what? Depth first search. It means we will start the journey from one node. If there is a connectivity to the another node, we will go to next node. Again, a next node will be having another connectivity to the further node, will go and traverse it. Okay. So depth way means what? If there is a connectivity continuous from one vertex to other to next vertex, will accordingly will go and proceed and find if there is no way to move further, then we'll try to go back by using backtracking. Okay, so let us see that. We can see these all things, how exactly you're going to perform the task in depth first search. So remember, depth first search is a method of processing or visiting vertices or edges of the graph in systematic fashion. It means we have to follow a proper rule. Accordingly, we are going to proceed and we are going to visit new vertex. A new vertex you are going to visit only when if that next vertex is connected directly with the previous vertex through an edge, or you can say path, direct path. Start an arbitrary vertex, that is called source vertex, and making it as a visited. It means what? Source vertex, from where you are starting journey, you are just mark it as a, that is the particular node is considered as a source, and hence we already visited. As we are starting the journey from your home, it means what? You are at home, that home is already visited, right? And remaining all other point of the cities we are going to visit it. On each iterations, proceed an unvisited vertex. And how are you going to find out unvisited vertex? If that vertex is adjacent node, adjacent vertex, it means what? That particular vertex is directly connected with the source vertex, then we can visit. The process in continue until dead end. As I said you, if there is no further path, that particular state is called dead end. From there, again we are going to backtrack. We are going to find out another possibilities of the node which we can visit, right? Once dead end is encountered, algorithm back up one edge to the vertex and it came from and tries to repeat the same process in order to find out another possibilities, right? And algorithm halts after backing up the starting vertex, right? So this process we are going to repeat it. Let us see that if you are doing this work, then what data structures you are going to use. As you are aware of type of data structures, from there we are going to use a stack as a data structures to implement DFS, depth first search. A stack is a data structures to be used for DFS concept. Now, you know that properties of stack. You know that property of stack is what? You can say that last in, first out, or you can say that first in, last out. As you can see that last in, first out, first in, last out means top inserted element will be deleted first, or you can say last inserted element will be deleted first, and we can say that first inserted element will be deleted last. So let us see that. Vertex pushed into the stack when it is reached first time, or vertex is popped when it becomes a dead end. Remember that when you want to revisit the vertex, suppose you are visiting the same vertex second time, then that particular edge or path, that particular edge between A to B is called back edge. That is called back edge. And all the edge or path which is going to be the part of your graph after applying DFS or BFS, that is called tree edge. Okay. So say after applying DFS and or BFS, if you are getting the path like that, A to B, B to D, D to C kind of things. So these all are called tree edge. It means what? These are the edge is a part of your answer. Let us see how you are going to perform DFS function, right? And before that, I will tell you the examples such a way that we can understand in better way. Example based on DFS. Right? See, here we have A, B, C, D, E, F, and here we have a G. Right? So we have a 7 vertex. We have 7 vertex. Now we are going to traverse it in by applying depth first method. So look how you are going to traverse it, and we are going to use a stack for that. So say we are going to use a stack as a S is a array. Hence we are going to create that many number of vertex. Okay. So say it is we are A, B, C, D. Just we are write it as a 1, 2, 3, 4, 5, 6, 7. Initially, we are not visited any vertex. Hence, we are making it as a 0. We are not visited it. Now we are saying that A is a source vertex. If you consider source vertex from where we are going to start the journey is A. It means we are saying that A is already visited. A is already visited. So, if A is already visited, then from there we are going to see that is there any direct path? Do you have any direct path? Yes. What is that? B. So, A is inserted into stack. Now, A to B there is a path, A to C there is a path, A to D there is a path. But first you are going to visit A to B because B will come first. No. From B, do you have any other path? Yes. B to C? No. B to D? No. B to E? Yes. So E will insert into stack. Remember the last in, first out, or first in, last out. So this is last in. So this will be deleted first if there is any problem. Now, how we are going to meet? The problem is what? When you are going to encounter with dead end. Now we are E. At the E, do you have path from E to other vertex? E to A? No. E to B? No. E to C? No. E to D? No. E to E? No. E to F. So F you are going to insert. From here, from F, we have F to G, there is a path. And top pointer will increase to the next positions. So initially top was here, next element, next element, next element, like this. No. We are at G. Do you have any path from G to other vertex? No. So we stopped here. Since we are not having any other vertex connected from the G, hence this particular position is called dead end. This particular position is called dead end. Now what will happen? Once you encounter with dead end, means you are going to backtrack it. So we are going to, we got, let us see that, here we got A to B, B to E and E to F and F to G. We got this. Now, while we are going to backtrack it, it means what? We are going to delete this node. Again, you are going to delete this. And from here, we are going to find out, do you have any other path from F? No, you don't have. Again, delete it. Do you have any path from E? No. If it is, then we can visit that particular vertex. But there is no other path from E, so we are going to backtrack it. Now we are at B. From B, do you have any other path? No. Then we are at A. Remember that there are 7 vertex. If all 7 vertex you have visited in first attempt, then there is no issues. That will be the final answers. But here in this particular case, now we are at A. So these all are only in a stack. We have A. Now from A, do you have any other paths? Yes. What is that? A to B is already been visited. Now we have A to C. So C we are going to insert into the stack. Okay. Now C, do you have any other path? Yes. C to F. But this particular vertex is already visited in previous iterations. It means we are keeping track of visited node. We are keeping track of visited node. What are the nodes are visited? So here we have A, B, C, D, E, F. So initially source is already visited. We are making as a 1. And B is also visited. What are the nodes we are visiting? We are just making, sorry, here it was C was remain 0, D was remain 0, E visited, and here F visited and G visited. C and D is remain 0. That is why what happened, we have started doing the backtracking. We went back to here. Do you have any path from A to C? Yes. If it is, C is visited earlier? No. In that case, we are going to make it visit. So C we are going to insert into the stack. Now from C, do you have any other path? Yes, F. But F is visited earlier? Yes. If F is already visited, then we are not going to revisit. It means this particular vertex, right? And this particular edge here is called cross edge, or you can say back edge. Because this particular vertex is already visited in previous iterations. Now we'll go back. It means there is no further path from C. We remove C. We go back to A. Do you have any other paths left? Yes, A to D. D is visited earlier? No, D was 0. Hence, we are going to visit D again. In this point of time, we can say that for A1, B is also visited, C is also visited, D is also visited, E is visited, F is visited, G is visited. It means all the vertex are visited from A. So, we are having C and here having D. Then, in that particular case, we can count 1, 2, 3, 4, 5, 6, 7 and all 7 nodes are visited from A. Hence, we can say that graph is connected. So, DFS gives solutions that graph is connected. And what is the second? To find a cyclic graph. A cyclic graph, when you will say that, means graph will not form the cycle. It means what? Minimal spanning tree. Which kind of tree it is? This is the outcomes. Is also called minimum spanning tree. Since weight is not there in edge, hence we are going to say that a spanning tree. So maybe you would have studied in what is called DS and DMS. What is a spanning tree? So a spanning tree is a graph in which number of vertex should be remain same. How many vertex you have, friend? 1, 2, 3, 4, 5, 6, 7. Number of vertex should be remain same in this, but it's not necessary that all the edges will present here. It's not necessary that all the edges will be present here. right? Hence it is a spanning trees. So you can see that there are many edges are missing, but all the vertex are present, and graph is not forming any cycle. Hence it is a spanning trees. So spanning tree is a cyclic graph in which number of vertex is remains same compared to the original graph, but number of edges may be lesser than the original graph. Hence it is called a spanning tree. So spanning tree is a outcome of DFS, and we are getting a cyclic graph. But a cyclic graph getting from DFS and BFS may not be same. Both the cases will have, there is a chances of 80 to 90% will have the different graph. But in some cases where ideal examples is there we can have DFS and BFS similar answers. So let us see that how your algorithm works for this. Let us see in this particular programs, or examples, you can call it as algorithms or program. Okay, so this is basically it is a program, so you can understand in better way, and you know that already C concept, DS you have studied. Hence, let us see that here all declarations you have done it. Here I enter the number of node, as in examples we have taken n is equal to 7, and then you are going to enter adjacency matrix I is equal to 0 to n, j is equal to 0 to n, and scan up. Remember that here array index is starting from 0. It means what? A is nothing but A is a 0, B is 1, C is a 2 kind of things, and we have entered here adjacency matrix, right? Then we are asking for the enter the source vertex, and for this we have entered A as a source vertex. So for this adjacency matrix, A is nothing but it is 0. 0 is a source vertex, right? So let us see first and write adjacency matrix for the given example. If this is the example A to B, B to C, C to D, D to E, E, F, G, there are 7 vertex. So if you are going to write how it looks like, say A is 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Right? So this is the vertex, and we are going to write adjacency matrix. A to A, 0, A to B. So here it is nothing but it is A, B, C, D, E, F, G. A, B, C, D, E, F, G. So for your understanding, A to B, there is a path. A to C, there is a path. A to D, there is a path. A to E, there is no path. A to F, there is no path. A to G, there is no path in our graph. Similarly, when you are talking about B to A, no. B to B, no. B to C, no. B to D, no. B to E, yes. B to F, no. B to G, no. Similarly, C to A, no. C to B, no. C to C, no. C to D. So we are going with the C. So C to D, no. C to E, no. C to F, yes. C to G, no. From D, D to A, no. D to B, D to C, no. D to D, no. D to E, D to F, D to G. E to all the vertex? No, we have only E to F. F to other vertex? We can see based on the previous graph, you would have noted down, we have F to G. And G to, do you have any path from G to other vertex? Look, no, we don't have any path from G, right? Hence, all vertex, all the values you are going to put it as a 0. This is the input. So A of ij, basically this is A of ij, we have read it. So we have to give the input in the form of adjacency matrix. So remember that here is a graph. This graph is converted into the adjacency matrix. Now what are we going to write it? We are going to write for loop, and we are going to keep track of V of I. Okay, so here says 0, 1, 2, 3, 4, 5, 6, and we have a 7. Initially, all visited of nodes we are making 0. Visited of all the nodes we are making 0 based on these statements. Now we have called it as a function called DFS A and B source. DFS A and B source. And since source we have already read it over here, right? And A is a source vertex. A is a source vertex. It means we are writing here V of source. V of A is 1. So V of 0 is 1. Why V of 0 is 1? Because we said that A is nothing but 0, B is 1, C is 2, like this. Here we are going to run one for loop. For I is equal to 0, I less than n, I plus plus. If A of source, what is source friend in this? Source is, as of now, source is 0, right? Let us see that. And I start from 0. So 0, 0. 0, 0, what is the value? Is it 1? No, it is not 1. Hence this condition failed. So we are going and increasing the values of I. So I must be increases. Because if this condition A of source I is equal to 1, visited of I is equal to 0. If that particular node is not visited, in that case, we are going to perform this task. So both the conditions to be true, because it is AND operator. Left side and right side, both the condition must be true. Then only we are going to call this function. Function calling itself. So still source is 0, but I for 0, 0 it is failed. So we are going to consider I is equal to 1. So I will keep track of I is 0, fail, I is equal to 1. If I is equal to 1, what will happen? A of source 1, A of 0, 1. What is the value of A of 0, 1? Is 1. If it is 1, then go in the other side. Visited of 1. What is that? I you are talking about 1. Visited of I, visited of 1. Visited of 1 is 0. Yes, visited of 1 is 0. Hence, this part is also true. Right side is also true. So we are going to call it DFS of A and VI. What is I, friend? I is 1. So we are going to make visited of 1 is equal to 1. So now this particular vertex is also 1. Right? But point to be noted is here, source is now 1. Source is now 1 because we are already traveled from 0 to 1. So we are at 1. Now again this for loop will start from 0 to all the vertex. So from 1 to 0, 1 to 0. What is 1, 0? It is 0. Right? So condition failed. I is increased to 1. 1 to 1, 0. 1 to 2, 0. 1 to 3, 0. 1 to 4 is 1. 1 to 4, 1, 4 is 1. 1 to 4 is 1. Adjacency matrix. Now visited of 4. Since 4 is 1, so we are going to check visited of 4. Visited of 4 is 0. Visited of 4 is 0. So both the condition is true, left side and right side. Hence, we are going to call DFS of A and BI again. And we are going to make visited of 4 is equal to 1. Basically, wherever you are having 1, it will go connectivity like B to E we have done. Now we have to go with E to other vertex, that is 4. Right? So let us see that E. First node is 0, 0, 0, 0, 0. Here, E to F there is a path. And what is that? Fifth node. So, since it is in adjacency matrix 4, 5 is 1. Whether visited of 5 is 0 or 1, it is 0. Hence, both the condition is true. Rest all the condition it was wrong. Right? So, we are going to visit this. Visited of 5 is equal to 1. We are at F. Do you have any path from F to other vertex? Yes. What is that? F to G. That is 6. And visited of 6 is 0. So both the condition is true. Hence we are going to do, this is gone. Visited of 6 is equal to 1. Now we are at G. Do you have any path from G? Look, G to A 0, G to B 0, G to C 0, D to D 0, G2E 0, G2F 0, G2G 0. So in previous place also you can see that from G we don't have any other vertex connected. Hence we are going to do the backtracking. Right? In that case, what will happen? We have already visited this node. Now, since function is calling itself, right? Thereafter, before this, visited of F to G. F to G, we have not made it here. 0 to 6, it's not required. This last one is not required because A, B, C, D, E, F, G. Okay, last one is not required. We have taken one extra. Now we are going to check. Do you have any path from G? No. F? No. E? Right? So basically what happened? These all ones where we are having it, we are focused on those parts. If not, then we'll go and backtrack it. And finally from B we don't have, from A we have a path. Again from A, we are going to traverse. Look, this function will return all the values after completion of these recursive functions. So what will happen here now? We are going to check from G you don't have any path, backtrack it. Do you have from F any path? No, backtrack it. E, do you have any path? No, we have seen in the previous example. And thereafter B, right? G, F, E, B, you don't have path. A, from A we have a path. So if you have A from you have a path, then we are going to check that. What is that? This is already address A to C. A to C means we are talking about 0 to 2 is 1. And whether 2 is visited earlier, visited of 2 is 0, visited of 2 is 0. Yes. It means what? This you are going to make it in the next iteration as a 1. Similarly, again you are going to increase the point, from C we are going to check. No, C to F is already there. Look, C to F when you are going to check, it is 1, condition is true. This condition is true. But right hand side if we go, C to F, C to 5, 5. Visited of 5 is 0 or 1. It is already 1. So this right hand side is false, left hand side is true, hence condition is false. So we are not going to do that. So similarly again we are going to do the backtrack, right? From 2 again 1, and from 1 we are going to check, okay, what is another possibilities? 1 to D, right? D is 3, whether visited of 3 is 0, visited of 3 is 0, hence we are going to make it as a 1. Look, in this particular case all are 1. If all are 1, I is equal to 0, I less than I plus plus, if visited of I is equal to 1, right? Count plus plus. So we count 1, 2, 3, 4, 5, 6, 7. If count is equal to n, and what is the value of n? 7. 7 is equal to 7, hence graph is connected. Remember that if number of visited node, visited of I, count value is lesser than the total number of vertex given in the graph. Hence we can say that graph is not connected. Graph is not connected. Look here, 1, 2, 3, 4, 5, 6, 7. Hence graph is connected. And I showed you very clearly from here we will go and backtrack it, right, to find other possible connectivities, right? So in this case, what we learn it, find out, spanning trees, whether graph is connected or not. So these all are the properties of DFS, right? Whether nodes are connected or not. What data structures are going to use? It is a stack. Outcome of DFS must be a spanning trees, right? It's never given you, a form of cycle. It is a cyclic graph, will get it as a outcomes. Now time complexity. Remember that earlier concepts we already discussed the time complexity. See, complete DFS function is running on this, right? And function is calling itself. Function is calling itself. So this is the DFS functions. And we are calling the functions. How many times we are going to run this? Remember, I is equal to n. N times we are going to run it, right? So here you are going to write the time complexity for this. and that will be number of vertex present in the graph plus E, number of edges, because we are keep track of edge, whether edges are present or not for each and every vertex. Edges are present or not for each and every vertex. Hence, time complexity for only DFS is V plus E. We can see that. What is the time complexity, friend? Time complexity for DFS, only DFS is theta of V plus E. Remember, but reading adjacency matrix is n square, as we have discussed in the previous examples, because we have two nested for loop. One nested for loop will give you n, another nested for loop will give you n. So n and n will multiply, hence it is n square. So this is the total time complexity. This is all about your DFS concept. So here under this we are going to discuss time complexity is V plus E, and for reading matrix input, time complexity will be theta of n square. To read the input, theta of n square, and overall, only DFS is theta of V plus E. Right? Thank you.